Hey everyone, and welcome. Today, we're jumping into the world of linear equations. Now, I know what you might be thinking, math class, flashbacks, but trust me, this isn't about that. Think of it as us learning how to crack codes, how to solve these little puzzles that are actually hidden all around us. We're going to build a mathematical toolkit together. Okay, so here's the puzzle for today. We've got two equations, but let's not call them equations. Let's call them clues. Our first clue is 7x minus 15y equals 2. And the second one, x plus 2y equals 3. Now, on their own, each of these clues has, well, a ton of possible answers. But when you put them together, they point to one single hidden solution for both x and y. And that's really our main question, isn't it? How do we take these two separate pieces of information and find that one magical pair of x and y values that makes both clues true at the exact same time? It's kind of like finding the exact spot where two different paths cross.
So, here's our game plan for building that toolkit. First, we're going to actually see the solution. Then, we'll get into two really powerful algebraic methods. One I like to call the clever swap, and another called the cancellation. And to finish it all off, we'll talk about how to pick the perfect tool for any puzzle you come across. All right, first up, let's actually visualize this thing. We're going to use what's called the graphical method. And really, the most intuitive way to start solving this is to literally see the answer. It turns out you can draw each of our clues as a straight line on a graph. And the solution to the whole puzzle? It's just the point where those two lines meet. Simple as that.
So most of the time, what you're going to see is this. Our two lines will cross at exactly one spot. That single point of intersection, that's our unique solution. It's the one and only x, y pair that makes both of our clues true. And whenever a system has at least one solution like this, we call it a consistent system.
But what if the lines are parallel? Like railroad tracks. They just run alongside each other forever, but they never, ever touch. Well, if they never touch, there's no point they have in common, which means there's no solution to our puzzle. We call this an inconsistent system, because the clues basically contradict each other.
And then there's one more possibility. Sometimes it turns out our two clues are just saying the exact same thing, just in a different way. When you graph them, it looks like one line drawn right on top of the other. We call these coincident lines, and since they touch everywhere, well, there are infinitely many solutions. This kind of system is called a dependent system.
Now here's the really cool part. You can actually predict which of these three things is going to happen without even drawing a single line. Seriously, just by comparing the ratios of the numbers in front of the x's and y's, you can tell right away if the lines are going to cross, if they're parallel, or if they're the same line. It's a fantastic little algebraic shortcut.
But, and this is a big but, graphing has a major weakness. It's awesome for understanding the idea, but it's not always precise. What if the answer isn't a nice, clean number like 2, 5? What if it's something messy, like the actual answer to our puzzle, which turns out to be 49 over 29, 19 over 29? Trying to pinpoint that on a hand-drawn graph? Yeah, nearly impossible. And that's exactly why we need some more powerful tools in our kit.
So, to get that perfectly precise answer, we need to get algebraic. Let's move on to our next tool, the clever swap, which you probably know as the substitution method. This is our first real algebraic tool, and it's built on a really simple but incredibly powerful idea. We're going to use one clue to redefine a piece of the other clue.
So how does it work? Well, first, we look for the simpler equation. In our case, x plus 2y equals 3. It's really easy to get x all by itself here, right? We just rearrange it to x equals 3 minus 2y. Now for the clever swap, we take this new definition of x and we substitute it into our other, more complicated equation. See what that does? It leaves us with one big equation that only has y in it. From there, we just solve for y. And once we have that value, we plug it back into our simple expression to find x. And boom, done. Now, sometimes when you're doing this substitution, something weird happens. The variables might just completely disappear. If you end up with a statement that's just always true, like 18 equals 18, that's your clue that the lines are coincident. You've got infinite solutions. But if you get a statement that's just plain false, like 0 equals 9, well, that's the math telling you the lines are parallel and there's no solution at all.
Okay, on to our next big algebraic tool, the cancellation, or as it's more formally known, the elimination method. This one is all about clever addition or subtraction to make one of the variables just magically vanish. And let me tell you, it is so satisfying when it works.
The process is actually pretty straightforward. First, you might have to multiply one or both of the equations by some number. The goal is to get the number in front of either x or y to be opposites, like a plus 6y and a minus 6y. Because then when you add the two equations together, that variable gets completely eliminated. Poof, gone. You're left with one super simple equation with one variable. Solve that, and then just plug your answer back in to find the other one. So, the big question is, which tool do you pull from your toolkit and when? Well, think of it this way. Substitution is your go-to method when one of the variables is really easy to get by itself, like the x was in our x plus 2y equals 3 equation. Elimination, on the other hand, is usually way more efficient when both equations are already nicely lined up in that standard form, just ready for a variable to get canceled out.
So there you have it. We've just gone through 3 really powerful methods for cracking these linear puzzles. Let's take a second to put it all together and formalize this mathematical toolkit we've been building.
Here it is, your complete toolkit. You use the graphical method when you really want to understand the relationship and get a visual estimate of the answer. You grab substitution when you see a variable that's just begging to be isolated. And you use elimination when the equations are all lined up, ready to be combined. If you can master these 3, you're ready for pretty much any pair of linear equations they can throw at you.
And that kind of brings us to a final, bigger thought. We've just spent this time learning how to find the one tiny point where 2 lines cross on a 2D plane. But what's really amazing is that these same principles, this idea of substitution and elimination, they're the foundation for solving systems with 3, 4, or even thousands of variables. This is the math that powers everything from massive economic models and network analysis to computer graphics and machine learning. The puzzle just gets bigger.